Let's talk more about separately excited DC generators. So this is the model again for the separately excited DC generator on the a circuit involving the armature circuit. These are the KVL equations, and take note that EA can be expressed as this formula here that we got from our introduction of DC machines. And for the field circuit, uh, this is the cable equation. This graph shows the what is called the terminal voltage characteristics of a DC generator. This shows the terminal voltage versus the load current. So this graph shows that at low load current, the terminal voltage is high, and it decreases as the load current increases. There are two factors, or even three factors, that cause this drooping of the terminal voltage. So these are the armature voltage drop, IARA, the brush drop due to the carbon brushes, and what is called the armature reaction. If you happen to review the material on the commutation problem that happens on real DC machines, armature reaction is a phenomenon that happens when the machine is loaded. So what happens there is that if there is a load current, the tendency of the effectivity of the flux in terms of producing the voltage is degraded. The higher the I sub L, the more severe is its effect on the internally generated voltage of the machine. So as I sub L becomes higher, the drop in terminal voltage becomes severe. Let's have a second problem for this module that pertains to a separately excited DC generator. So on the previous problem that we had in the introduction, um, let's say that the machine is connected to a 15 ohm load. So let us determine that what is the terminal voltage, and then what is the armature current that comes out of the armature. Earlier we saw that we got a terminal voltage of around at 373 volts if the machine has no load. So now that it has a load, we would expect a lower voltage uh, that is lower than 373. So we simply use the trivial equations for the um, armature circuit. So doing that, that will give us an armature current of this much, and from this we could compute our terminal voltage, which we obtained to be 366. So it is indeed lower than the one we have if the machine is not loaded. We could also use a different approach uh, by using the voltage divider technique. So we have already a sub A, and to get P sub D, all we need to do is use the voltage divider, and that could provide us a quick answer of 366 as well. Normally, in generators, we would want to be able to control the terminal voltage of the machine. So for a separately excited DC generator, what are the parameters that we can vary to control the terminal voltage? So we could vary the speed of rotation of the prime mover. So based on the equation for terminal voltage, the terminal voltage has a direct, or the speed has a direct effect on the terminal voltage of the DC generator. So we could vary this, and that would change our terminal voltage. We could also change the field current, which is the more common way of doing it, since usually generators run at a constant angular speed. So if we vary the field current, that should vary the flux produced by the field circuit. As long as the uh, field poles are not saturated, we can have a decent amount of change for any change in the field current. So the magnitude of the flux depends on the amount of field current, um, assuming the core of the field poles are not uh, saturated. So far, what we have done in our examples is to show the characteristics, uh, the linear characteristics of the separately excited DC generator. Here, on the succeeding parts of this video, we're going to cover nonlinear analysis. Um, this is important because the internal generated voltage of a DC machine is usually affected by the saturation of the field poles. So we need to take this into account when we do the analysis. In addition to that, EA is also affected by the armature reaction due to load current. As explained, the armature reaction occurs when the generator starts uh, or accepts load, or there is a load current, and it becomes severe if the load current is large. Um, there is also the effect of variation in angular speed of the rotor due to the load current. So what is meant by this is that the speed of the, or the angular speed of the generator usually tends to slow down if the load is becoming uh, large. And in fact, if you don't have a speed regulator, this the speed becomes the change in speed becomes severe, that it greatly affects the terminal voltage of the um, generator. The magnetization curves that we used in our examples is a plot of the internally generated voltage and the field current at no load and at a specific angular speed. This curve uh, has already taken into consideration the effects of saturation of the feed poles, but it does not uh, take into account the armature reaction because it is that a plot at no load. So in our succeeding examples, we will try to incorporate armature reaction in our examples to see how these phenomena affects the characteristics of the machine. For speed variation, we won't be covering this because in reality, generators are normally equipped with speed regulators, so we don't have to worry about the speed changing with load. So how do we factor in the effects of AR in our computations? So we show this by another example. So here we have a separately excited DC generator. It has a rating of 172 kilowatts. So this is the maximum wattage that it can handle. And at that rating, or that is the rating when its terminal voltage is 430 volts, and with that, it will deliver a current of 400 amperes at this rotational speed of 1800 RPM. So the details of the field circuits is also given. So the field circuit has 1000 turns. The field windings has 20 amps, and in series to that is a variable resistor that varies between 0 and 300. The armature windings has a zero point zero 0.05 ohms of armature resistance. Also given is the magnetization curve for this machine. Okay, so the first question is if the variable resistor that is in series with the field circuit is at 63 ohms and the generator's prime mover is driving the generator at 1600 revolutions per minute, what is the generator's no load terminal voltage? So the answer there is actually is 382. So since the question in A is no load, armature action has not yet come into effect here. Now in B, what would be its voltage? That is the terminal voltage. If there is a 360 ampere load, assume that the generator has a compensating windings. Compensating windings are part of the armature circuit, and is a technique to overcome the effects of armature reaction. So if you have compensating windings, it is as if there is no armature reaction even if you have a load. Okay, so that is for letter B. So again, letter B is although it has a load, we assume that there is no armature reaction there because of the compensating windings. The third question is the same as B, except that there is no compensating windings, so it does not have compensating windings. So in C here, the armature reaction will come into effect. So let's see how it affects the terminal voltage. And letter B, what adjustment can be made to the generator to restore its terminal voltage to the value found in part A. So this really means that uh, after C, our terminal voltage becomes severely decreased because of um, the armature voltage drops and the armature reaction. And we want to know what adjustments can we do to restore the terminal voltage with the same value that is found in letter A, which is really the voltage if we don't have any load. So what are we going to do? So, well, the answer is to decrease the value of R sub V. And E is, now that we know that R sub V should be decreased to increase the terminal voltage, what is that value of R sub V? And what is the corresponding field current for that value of R sub V? So actually the answers are here. Okay, so let's go over with the solution. So first we compute the value of R sub F. So R sub V is tuned at 63 ohms. So plus the internal resistance of the field windings, you will get 83 ohms. Then we go on to compute uh, our field current. So our field circuit is excited by a 430 volts. So we get 5.18. From the magnetization curve, we look for 5.18. It is, well, it is somewhere here. And we notice that we will get a voltage which is 430, which is here. However, 430 is for 1800 RPM. So we normalize that value for 1600 and we get 382 volts. So at no load, our EA is 382 volts. Uh, that is for a speed of 1600 RPM and IF of 5.18. Now, since this is no load, we could say that our terminal voltage is roughly the same as the internally generated voltage. Although it is slightly yes, but it is safe to assume that our terminal voltage is the same as our EA. For letter B, we put a load to the DC generator, a load of 360 amperes. And since it has compensating windings, the effect of armature reaction is negligible. Hence, we should get the same um, internal generated voltage of 382 volts. And with that, we could compute our new terminal voltage. Uh, so we got here 364 volts. So the terminal voltage is getting lower. So earlier we have 382 volts, and then we put a load of 360 amperes. Now it's down to 364 volts. For letter C, now we assume that we don't have compensating windings. So the effect of armature reaction will kick in and will slightly degrade our internally generated voltage. Uh, so how are we going to determine our new EA? So the technique here is to determine a new value for I sub F. Uh, that would be the actual value minus this one. So this one is 450. There is the uh, armature reaction. This figure here is given. I think this is 450 ampere turns. So that is the armature reaction for 360 amperes of load. Take note that this armature reaction uh, becomes larger as the load current becomes higher. So for 360, it is 450 ampere turns. And since there are 1000 turns in the field circuit, we divide that figure by 1000 and we should get something out of it. Then we subtract that result from our actual I sub f, and that will give us a lower value for I sub f. So what really is happening here is that we try to squeeze in the effects of armature reaction by decreasing supposed to be the value for I sub f. Although the actual value of I sub f is still 5.18, so that we would be able to um, consider the effects of armature reaction. So once we get a new value of I sub f, we then go back to the magnetization curve. So here is 4.75, and from there we get a value of around 410 volts for EA. However, that is again for 1800, so we normalize for 1600 and we get 364 volts. Then for our from our KVL equations, we could recompute the terminal voltage and we will get 346 volts. Take note, this is lower than what we have in letter B, because in C we already have an armature reaction. For letters D and E, the question is what should we do to restore the terminal voltage to a value the same as the voltage when there was no load. Um, we do this because our terminal voltage has decreased so bad that we need to increase it. So the way to do that is to decrease the value of R sub B. So to compute for the value of R sub B, so we use the KVL equations again, and this time we let V sub t equals 382, and compute back for the value of A sub A, and that should give us a 400 volts. However, we're dealing with a machine that runs at 1600 RPM, and we need to normalize it to 1800. So we go backwards here so that we could use the magnetization curve. So normalizing it to 1800, that should give us a 450 volts. And from the magnetization curve, a 450 volts corresponds to an IF of around 6.15 amperes. Okay, so and then using Ohm's law on the field circuit, we should be able to get a value for R sub B, which is around 50 ohms. So 50, a value of RB equals to 50 ohms is what we need in order to restore back our terminal voltage to 382, which is our voltage when we don't have a load. Okay, so it's also interesting to note that if we try to maintain this value bar sub B and then we cut off our load, what would happen to our terminal voltage? So if we do that, take note that at a value of R sub B equals to 50 ohms, we have an I sub F of 6.15, and that means we get an EA of 450, and that is for 1,800 RPM. We normalize it again to 1,600 RPM, and we should get an EA of 400 volts. And since we don't have a load, that means that our terminal voltage would be 400 volts if our R sub V is 50 ohms. So it would shoot up our uh, terminal voltage drastically, and to decrease it again, we need to adjust our R sub B back to 63 ohms. So that's it for a separately excited DC generator, and on our next video we will discuss self-excited DC generators.